Every day, we use plastics without even thinking. From the bottle we drink from,
Thank you.
to the cup that holds our coffee. To the bags that we carry home. But these materials don't just disappear. Over time, they break down into microplastics, microscopic fragments that have spread into nearly every part of our environment. They're in our water, our food, and even the air we breathe. And now, researchers have found them inside of us, accumulating in the small intestine, where they can disrupt the gut barrier, trigger inflammation, and damage intestinal cells. Studies have even linked microplastic exposure to oxidative stress, DNA damage, and potential effects on the nervous and cardiovascular systems. What initially began as an environmental issue became a human health issue. And that's where our project begins.
Our team took a multidisciplinary approach to understanding the problem of plastic waste by exploring the critical link between microplastics and their impact on human health. We conducted a thorough life cycle assessment of microplastics to truly understand that they are not just in the environment. They're not only in landfills, oceans, and waterways, but they're also inside of us. Our human practices team met with researchers from various fields, such as geosciences, environmental sciences, biology, neuroscience, chemical and biomedical engineering, to ensure our solution makes a positive and measurable impact. After interviewing with researchers and discovering the negative health implications that can be associated with microplastics, our main goal was keeping our solution human health focused, so we decided against a plastic alternative. We wanted to introduce something more novel and impactful to the issue, so we researched degradation and aggregation methods. However, through interviews with experts, we found that degradation can leave behind toxic byproducts. Because of this critical safety concern and our commitment to a safe and beneficial outcome, we pivoted away from degradation and towards aggregation. Recognizing the full effects of microplastics, we're tackling the problem from two different angles. First, we're developing a targeted therapeutic within the gut, and the second is by spreading awareness, education, and outreach. We can combat the issue of microplastics, inform more people, and potentially influence future policymaking within Florida.
Our team's human practices work would go on to shape every single part of our project, from design to development, and how we engage with our community.
Armed with an HP-guided understanding of essential concepts for our project, such as microplastic health effects, what a functional and convenient product would look like from a consumer standpoint, as well as input from experts on what a solution would potentially look like, we were able to go ahead and formulate a high-level design. And so how that design manifested for our team was in the probiotic strain E. coli Nissl 1917, and it performed surface display of fusion protein. And so that fusion protein composed of the primary functional component, the plastic binding peptide, as well as a flexible linker protein to give it some room to move around and have more room to bind. And finally, an anchor protein to display it on the surface of our chassis. And so the idea was, as microplastics kind of pass by our chassis in the small intestine, or in the ileum of the small intestine, which it's colonized, it would be able to bind multiple of those microplastics passing by and prevent them from getting into the bloodstream.
Initially, our team's design was meant to target PET. However, after interviewing experts, we realized that polystyrene is a more studied threat to human health and was more feasible to use in the lab. So we restructured our design around this. We explored different types of binding molecules, such as nanobodies, deactivated enzymes, and peptides. After basing our design after polystyrene, we decided that utilizing peptides would give us the best flexibility for modeling and expression. In our initial design, we created two generator variants, one with and one without the linker, to see how the length of the peptide might affect expression and binding. Our modeling team also used AlphaFold 3 for predicting peptide folding structures, as well as GROMACS for molecular dynamics simulations of peptide behavior. This simulation video, created by our modeling team and posted on the iGEM video universe, visually simulates how our peptide would interact with polystyrene. Our team's modeling would go on to influence our design and build cycles greatly, giving us confidence that our selected peptides would bind.
We needed to see if the whole basis of our project, these plastic binding peptides, would actually function in the wet lab.
With the foundation set by modeling and design, we began constructing our plasmids. Our original twist kanamycin vector failed due to 10 consecutive adenines in the 5' UTR. So, after advice from our PI, we truncated that region and introduced the T7 Max promoter with an adenine-rich spacer to enhance polymerase binding and transcription efficiency. We built a new backbone, our generator skeleton, BBA252JX551. This redesigned skeleton became the framework for our new constructs. During this build process, our entire team underwent full lab safety training with Dr. Arce at the FAMU FSU College of Engineering, learning proper PPE use, biosafety cabinet protocol, and emergency procedures. We ran our samples on a 16% tricine gel, ideal for detecting peptides as small as 3 kilodaltons. Using silver nitrate and Kumasi stains, we expected to see faint bands, but nothing. We repeated the test, this time purifying the lysate and performing an anti-His Western blot, checking for aggregation. Still, the 3 kilodalton band never appeared. Despite verifying that the T7 Max promoter we introduced was working, our construct failed to express detectable levels of peptide. However, science is built on iteration. With guidance from our advisor, Alana Chang, we revisited our initial designs to improve expression and solubility. We added BD Sumo and 12 histidine tags, incorporated a superfolded GFP reporter for visualization, and shifted to a linear design for faster synthesis. We built 3 new PS binding units, K, L, and M, all synthesized through Twist Bioscience. Expression was tested using the NEB Express cell-free system under careful supervision and safety protocols. Finally, we tested our constructs through sumo protease cleavage and vacuum filtration binding assays. Protein yield was measured using a Bradford assay, and results, supported by our modeling, will be shared at the 2025 iGEM Jamboree.
Our product and service is Plastipeutics, a digestible product that detoxes the gut from microplastics. Plastipeutics sets the foundation for the future of detoxing microplastics from the human body and educating the world on the danger of microplastics. Plastipeutics' mission is to pioneer a future where our capsules and software is in everyone's home and is a household tool to reduce the harmful plastics that accumulate within your body, servicing everyone from the eldest in the family to the youngest. Our method is simple and easy. We plan to provide access to our product via several online retailers that sell health and body positive supplements. We also sell our product directly to our consumers.
For $30 a month, customers receive 30 capsules in a plastic-free container, along with access to our companion app. This app includes a store where users can purchase the product and refills directly, a meal input feature that estimates microplastic consumption using data from scientific literature, and a community board to share updates, developments, and engage with our growing network.
As of now, once we start this market, our team hypothesized that if we reach at least 1% of our market, we are introducing about 170,000 people to a new future and profiting as a company about $64 million within that year.
After iGEM, our next step is to finalize intellectual property and licensing with our university's Office of Commercialization. From there, we'll evaluate our resources, including team expertise, lab equipment, and funding, to plan how to continue research and development and develop a proof of concept for future accelerator applications.
Today is the third annual Tallahassee Biotechnology Expo. This is our third year running the expo in partnership with the Challenger Learning Center with FSU iGEM. We have so many different researchers here, exhibitors, and students from the Tallahassee community. We've had over 300, 400 people come today, over 15 exhibitors, all to just showcase synthetic biology, genetic engineering, iGEM itself, and just STEM and biotechnology to the Tallahassee community.
I just said, look, we've got a great venue for this. They did all the hard work in putting together the programming and the speakers and the tabling, and so it's gotten better every year.
At the third annual Tallahassee Biotechnology Expo, hosted with the Challenger Learning Center, we introduced families and students to the world of synthetic biology through interactive exhibits and IMAX presentations about microplastics and innovative biological solutions. We also partnered with Who We Play For, a nonprofit dedicated to preventing sudden cardiac arrest in young people by providing free heart screenings. This collaboration brought a vital public health component to our event and showed how science can directly save lives. To ensure this tradition continues, our team documented everything, creating a full resource kit with planning materials, surveys, and layout designs, so future FSU iGEM teams can build upon our efforts and continue our legacy. Through our outreach, we've sparked curiosity, strengthened community ties, and inspired others to join the effort towards a cleaner, healthier future. For the bronze medal requirements, our team created a Visio video tutorial to teach iGEM teams around the world how to use S-Ball for genetic circuit design. We also characterized the T7 Max promoter, helping future teams understand its efficiency in both linear and circular DNA systems. For our silver medal, we demonstrated engineering success through multiple design iterations, learning from our early failures and improving with our new Sumo designs, which are currently being tested. During our entire iGEM cycle, our human practices, from outreach to real-world impact, guided every step of our approach. Finally, for the gold medal requirements, our team built upon human practices, modeling, and entrepreneurship work. Science is about more than data and discovery. It's about people, their creativity, persistence, and hope for something better. What began as an idea became a shared mission: to use synthetic biology to tackle the growing problem of microplastics and protect the health of future generations. Every step, in the lab, in our community, and with each other, brings us closer to a cleaner, healthier world.